Hello everyone, welcome to the session. In this session we'll see motion of rotation. Motion of rotation occurs when all particles move in a concentric circular path with a common center, and this is your axis of center. And now around this all the particles move in a concentric circle, right? All the particles of a particular rigid body. And now this axis of rotation or this particular center may lie inside your body or outside your body. We'll see that clearly. See, for example, consider a rigid body. Now here we have a point A, and now here we have a point B, and this particular body may revolve or rotates about this particular point. It will rotate about this particular point in this direction, right? Or it may be having like point here, and now the total rigid body will rotate in this direction about this fixed axis, right? And moreover, and this axis may lie inside your rigid body, or it may also lie outside the rigid body. See, about this particular point, the total body from link, if you take the point A here and take the point B here, and this point is outside of your rigid body, and this will rotate like this about this fixed axis. And now for all the fixed axes in motion of rotation, we have zero velocity. We already seen this concept in the instantaneous center, right? So for all the axes of rotations, we have zero velocity. Okay, and now when your body is rotating, we call it as angular motions, right? And the previous case we've seen all the linear motions. But here from the rotation, these are angular motions. And for these angular motions, we have velocity, we have acceleration, right? We have a velocity and the acceleration, but these velocities and accelerations are angular velocity and angular acceleration in angular motion concept or in a motion of a rotation. But coming to the linear motions, we just called a linear velocity and linear acceleration. Then what is the difference between these linear and the angular motions, and what is the difference of notations that you are going to use in this motion of rotations? We'll see all those, and these are the notations are particular for the linear motions, and these are the for angular motions. And this is your initial velocity in the linear motion. But coming to the angular motion, it is omega naught, omega 0 or naught. Okay, and coming to the final velocity, this is omega. And coming to the acceleration, and your angular acceleration is alpha, and this is linear displacement, and this is angular displacement, which is theta. And we already seen the equations of motions for all the linear motion problems, right? And now coming to the angular motion problems, we have these angular motions. These are the equations of rotations. These are the equations of linear motion, and these are the equations for angular motion or rotation. And this is for velocity, and this is for the displacement, which is s equals to ut plus half at square. And coming to angular motion, this is theta equals to omega naught t plus of alpha t square. And in the same way, we have a differential equation for the velocity, right, which is change of displacement with respect to the time. And coming to the angular velocity, this is change of angular displacement with respect to the time. Coming to the angular acceleration, it is change of angular velocity with respect to the time. And we have few more formulas for this, which is like coming to the force causing the motion, and this is the equation for a linear motion. Okay, and this is the Newton's second law of linear motion, and this is the Newton's second law for angular motions. And for the moment, we have mass into velocity, and coming to the angular motions, we'll write it as angular moment, which is I into omega, which is moment of inertia, into which is angular velocity. And coming to the kinetic energy, this is of mv square for the linear, and coming to the angular motions, we have half into moment of inertia into velocity square. And for all the rotatory bodies, we have revolutions per minute. All the revolutions will be, all the angular motions will be revolution per minute. If you want to convert that one revolution per minute, we can equalize to 2 pi radians per minute. And for n revolutions, it is 2 pi n radians per minute. And angular velocity equation in terms of radians per second is omega equals to 2 pi n radians per second. If you want to convert that minutes to seconds, just divide that by 60. We'll see a small problem on this rotation of bodies. Here we have 600 mm diameter of flywheel is brought uniformly from rest. It starts from rest, okay, where your initial velocity is equals to 0, but it is a angular one. So angular velocity, which is initial angular velocity, is equals to 0, and the speed of 350 rpm in 20 seconds. And determine the velocity and acceleration of a point on your rim 2 seconds after starting from the rest. See, here the starting time is 0, and here it is like 2 seconds. At this particular point, what is your acceleration and the velocities we required? But it is moved for how many seconds? 20 seconds. Okay, it is moved up to 20 seconds. And next, coming to the solution, see, the radius of your flywheel is 600 by 2, which is 300 mm, and convert that mm into meters. And your initial velocity is angular velocity is 0, and the final angular velocity is 2 pi n by 60. Why? Because we have the revolution or speed of that in revolutions per minute flywheel, which is 36.652 radians per second. And now coming to the angular acceleration, it is change of angular velocity with respect to the time, and final angular velocity minus initial angular velocity is your change in angular velocity. We have these two values, and if you substitute here, and this is per time t. Okay, what is the time for? Okay, take for 20 seconds, and this is your final acceleration. But what we require is and the linear acceleration and the linear velocity at 2 seconds. But first we'll see what is the angular velocity after 2 seconds, and this is your final angular velocity, which is initial velocity plus acceleration into time. And if you substitute those values, and these are the radians per second, which is 3.66 radians per second, that's your angular velocity, which is final angular velocity. But after 2 seconds, we require this initial linear velocity and the linear acceleration. For that sake, we have a relation with respect to your linear and the angular velocities, which is linear velocity is equals to angular velocity into r. If you substitute those values, you are going to get 1.098 meters per second as your linear velocity. And when we have a rotation, and when there is a change in velocity and there is a change of direction, because of that we have the tangential acceleration and the normal acceleration. So we have to find those two accelerations, and this is your tangential acceleration, which is angular acceleration into radius, and by this you are going to get 0.549 meter per second square. And we know the normal component of your acceleration, which is v square by r, and we already got this v. We already know the r value, which is radius. By substituting those values, you are going to get 4.018 meters per second square. And coming to your final acceleration, it is the square root of normal acceleration square plus tangential acceleration square. After substituting these values, you are going to get a linear acceleration, which is 4.055 meter per second square. We already seen about these tangential acceleration and normal acceleration in the previous session, which is currently here. Thank you.